Hello everybody. In the last session we started discussion on the phasor analysis, analyzing the circuits by means of phasors. In this session we shall consolidate on those concepts and try to use it on real circuits like the R, RC, RLC circuits and see what information we can gain from the phasor diagrams. Till now in the last session I have been interchangeably using phasor and vectors. So, before going further I would like to put forth to you the question, what is the difference between a vector and a phasor? So, we have two terms here, one is the vector and the other is the phasor. What is the difference between the two? Because when we saw in the other session, that is the last session, we had been drawing vectors and we have been using the term vectors in the temporal coordinate system, vectors in the spatial coordinate system, so on and so forth. The space vectors, space phasors, we have been using these terms interchangeably. But before going further, it is nice to understand what is the difference between them, even though it may be a small difference. Now, in the case of the vector, as we know, it is represented by an arrow which has an amplitude r and a direction as given by the arrow with respect to a reference. With respect to a reference, the direction is specified. So, if I have a reference as shown dotted, with respect to the dotted reference, the vector or the vector arrow is at an angle theta. So, this is usually represented as r angle theta or r e to the power of j theta. Okay, this is the polar coordinate representation. So, this is a vector where r here is an amplitude. In the case of a phasor, phasor also is represented by an arrow. This also has a direction with respect to the reference. Let us say I have a reference here. You can have a direction theta with respect to the reference, and it has also an amplitude, and let me call that as Rp to distinguish it from the vector amplitude R. The difference lies here in Rp. Instead of using the exact vector amplitude there, in most of our sinusoidal analysis, we would like to use the effective value of the wave shape rather than the peak value. So, the Rp here represents actually the RMS quantity. This is a RMS value, that is the root mean square value. So, effectively the phasor and vector look the same, but in the amplitude, whereas in the case of the vector diagram, the vector amplitude is the exact vector amplitude. In the case of the in the case of the phasor, the vector amplitude or the amplitude of that arrow is the effective value, which is the RMS value of the signal. That is pretty useful in sinusoidal circuit analysis, because we use the RMS value in almost all cases for power the heating content, I RMS square R, all those things. So, therefore, the phasor diagrams are extensively used in sinusoidal analysis. So, when we say phasor, remember that the amplitude is RMS in value. When we say vector, the amplitude is the exact peak value of the vector. So, with that a small note, let us go back to what we were doing in the last session. So, we had a circuit, the familiar RC circuit, which I am writing down here for clarity. There is a V I, there is a R, there is a C. C is going to give a capacitive reactance which is minus 1 by sorry, I will rub this, I can just put it as here minus J X C. Now, there is a current through the circuit and that current is I. Now, for this circuit we drew the phasor diagram in the last class, but remember that we chose a reference. The reference axis in the spatial coordinate system that we chose was along the VI direction. And here we see that the current is leading the voltage and therefore, we have the current I. Now, the voltage which is in phase, that is which is I into R, is going to be along the current vector. So, this is going to be I R. Now, the voltage across this is going to be I into X C, but there is a minus J, which means minus 90 degrees rotation, and that is going to, this is going to be a minus 90 degree rotation, and this is I X C. This is the phasor diagram that we obtained in the last class. Just to recap, note one point, this J here can be treated as an operator called the J operator. Whenever you have multiplication by J into something, then this quantity is going to be phase shifted by 90 degrees anti-clockwise. Internationally, there is a convention for signs of rotation. Anti-clockwise is positive direction for rotation, and clockwise is negative direction for rotation. Now, a plus J is going to give you anti-clockwise plus 90 degrees rotation. So, if a vector is in this rotation, in this form, let us say now you apply plus J, that is it is multiplied by a factor plus J, then the vector will be rotated anti-clockwise or the positive direction by 90 degrees to get this to get this vector. Now, if you had minus j into something, then that is going to result in negative direction, which is clockwise. So, if I had the same vector in this form and on this you operate on minus j, that is going to rotate minus 90 degrees clockwise to obtain this new position. So, remember that plus j into something is going to cause a rotation of the vector by plus 90 degrees, which means anti-clockwise direction plus 90, a minus j in the factor is going to cause a rotation in the clockwise direction by 90 degrees, because minus j is negative direction for rotation. Now, going back to our circuit here, let me just copy this circuit and all these things. Go to the next page. Yeah. Now, you see here that we had used the VI direction as the reference, that is the reference in the spatial coordinate system, but we could as well use the I direction also as the reference. It is up to you to choose a particular vector as a reference, but the relative position still would remain the same. So, let us say this direction here represents the I direction. The I vector direction, which means now the I is, the current I is like this. Notice the correspondence here. Now, this being a capacitive circuit, the I leads the voltage, the input voltage. Therefore, the voltage, input voltage is lagging the I. So, I have the input voltage which is lagging the I, this is going to be VI, and that is formed by, I will be having I into R this is the vector in phase with the I, and then I into G minus j x c, minus j means minus 90 degrees rotation. So, this has to go, this is I x c, this completes to give you the VI. See that these two are similar vector diagrams or phasor diagrams, only that here the reference was chosen as the VI direction, the VI vector direction as the reference, whereas here the current vector or the I vector has been chosen as the reference. However, the relative phase shifts between these two still is maintained. Relative phase shifts between this and this is still theta, and that is maintained. Now, here what is the angle theta? Look at this, theta is tan inverse of minus x c by r. Minus here to indicate that it is minus j, the minus j x c term, and minus here also indicates a negative direction for the angle of rotation theta, or the absolute value of theta would be tan inverse of x c by r. Now, here let us make a small introduce a new component, a new variable into this picture here, and that is Z. Now, Z is called the impedance. Also in ohms. R is the resistance. This also is in ohms, and X is the reactance, also in ohms. The impedance is actually the vectorial sum of R plus J X. How does this come about? So, when you look at this phasor diagram here, could be either the VI direction phasor diagram or the I reference phasor diagram. This is I into R, this phasor is IXC, this phasor which completes the Kirchhoff's voltage law is I into Z. So, therefore, let me choose that. Therefore, let me remove the i's. Let me erase the I from this. So, you have an R, an XC and a Z. So, which means I could write it as an R and exactly 90 degrees, you have XC and then you have a Z. You have equivalently 3 vectors and there is a theta here, of course, same theta as would have been here. Or you could write it as in the current axis direction, that is, I have an R just vertical down XC, which is 90 degrees with respect to this horizontal axis, and then from here we have the Z, and this angle is theta. It is just this repositioned here with this as the reference, now taken horizontal. Now, this triangle is called the impedance triangle. This is called the impedance triangle. So, if this is R and this is XC, this is Z, and Z will be equal to square root of R square plus XC square by applying the Pythagoras theorem. So, this is nothing but root of r square plus x c square. As x c is orthogonal to r, we could also write in complex form z equals r minus, let me put it as plus, minus j into x c. Look at this minus j operator here. Minus j means that it is going to rotate that vector by minus 90 degrees, and that is what is done here. So, this results in r minus j x c. This is the impedance, which is the impedance of the circuit as seen from the input terminals. The impedance triangles are obtained when we are applying the Kirchhoff's voltage law to the loop. What happens when we try to apply Kirchhoff's current law? So, let us take a circuit which looks like this. So, I have a circuit like this. So, you have a C and a R, and you have a, instead of having a voltage source, now I am going to have a current source. Let me take a dual of that circuit. So, I am going to have an I, this node is going to have a potential V, this is of course C and R, and this is going to give you an impedance or a capacitive reactance minus j x c. Now, let us draw the phasor diagram for this. Let us first have an axis. So, all our phasor diagrams are in the spatial coordinates, and note that the phasor diagrams in the spatial coordinates can be mapped onto the temporal coordinates, which will result in the actual wave shapes, and the phasor diagrams will give you a picture at an instant of various wave shape relative to one another taken with respect to some reference. So, let us have a reference. Now, this is the horizontal axis. We can of course decide what reference that we would like to have. Now, let us say we take the reference here as the current. Let us take the reference here as the current direction, that is I direction. Okay. Now, what is the relationship of V with respect to I? Now, we know that the current leads the voltage in a capacitive circuit. So, in this case the voltage will lag, the voltage will lag the current. Now, let us come back and just see how it reflects here. Let us have a look at KCL that we want to apply here. We want to apply KCL. To the loop we apply KVL. Now, if we apply KCL there, V by minus j x c, that is the current through the capacitance, plus V by R, that is the current through the resistance, should equal I. Isn't it? This is equal to J V by X C plus V by R. This is nothing but multiplying the numerator and denominator by J. So, in the denominator it becomes minus J square, which is 1. So, J V by X C plus V by R. So, we have let me put it like this. We have a voltage V direction. So, in that V direction, there is one vector which is along it, and I will call that one as V by R. Now, V by R plus J V by X C. Now, V by X C is multiplied by J, which is along this, it is plus 90 degrees. So, anti-clockwise direction 90 degrees, which will be like that. This is V by X C. That is going to give you I, isn't it? Now, let us, we have the one in which is in phase with V by R, and then you have V by X C, and this I should be equal to V by Z. Now, here you can remove that and that being common. So, we will end up with a triangle which is like that. So, this is the triangle that you will end up with. This is 1 by R, this is 1 by X C, this is 1 by Z, and you have some angle theta here, same as the angle theta here. What is 1 by R? R is resistance, and therefore 1 by R is the conductance, which has a unit of mhos. 1 by ohms dimension is mhos or Siemens, and this has a symbol G. Likewise, 1 by X C is called susceptance, and it has a symbol B. Now, you see here, this is 1 by R, which is G, 1 by X C, which is B, and 1 by Z will be, let us say, Y. So, Y is called admittance. and this is called the admittance matrix triangle. Now, in the admittance triangle, we have Y, we have G, and we have B. This is theta, and Y is equal to G plus J B. Now, see here, the impedance was resistance plus J reactance, admittance is conductance plus J susceptance. If there is a capacitive reactance, that has a negative sign, minus J X C, a capacitive susceptance. So, this capacitance has a reactance which is minus J X C, or a susceptance B, which is 1 by this, which is equal to J B, and an inductance, and that is positive. And that is why in a capacitive circuit you see the rotation which is positive here. And in the case of an inductance, it has a reactance which is JXL and a susceptance which is 1 by JXL, which becomes minus JB. We can give a subscript L here and a C here. So, this is the admittance triangle, and here also theta can be obtained using theta equals tan inverse of B by G. This is the angle from the impedance matrix between I and the voltage phasors. So, you see that if we use KVL for solving a loop equation, we would land up with an impedance triangle. If we use KCL to solve a nodal equation, node voltage equation, then we would land up with an admittance triangle. There is one more triangle which you will come across, and that is the power triangle. Let us see what this power triangle is. Let us go back to our now more common RC circuit. So, we have the R and C as usual, as it looks here. You have the R, you have the C, you have the voltage, input voltage, and minus j x C is the impedance that this capacitance provides. Now, let us take a reference which is the V reference or the voltage reference. Now, there is a current which is flowing through the circuit, and that is I. Now, this being a capacitive circuit, this current I has to lead the voltage. Now, here there are two important things that to be noted, and let me also have the vertical orthogonal axis here. The projection of I onto the V axis is called I alpha, because this V reference is called the alpha axis and this would be the beta axis, and the projection of this I onto the beta axis is called I beta. So, I alpha is in phase with V, I beta is orthogonal to V. Now, multiply all these with the voltage amplitude V. This being a phasor, when you are multiplying it with V, I am meaning that we are multiplying by with RMS quantities. So, I alpha RMS with V RMS, I RMS with V RMS, I beta RMS with V RMS with the same. So, relatively only the vector amplitudes only will change. So, what would happen is I have V into I beta, V into I, V into I alpha. That quantity which is in phase with the voltage V into I alpha is called the active power. That quantity which is orthogonal to the V axis or the alpha axis, which is having an amplitude V into I beta, is called the reactive power. This quantity V into I, the resultant of the active power and the reactive power, is called apparent power. This has units of watts. This is called volt amp reactive, VAR, VAR. This is simply VA. So, this triangle, if we write it here, we have watts, we have reactive VA, and the resultant which is VA. and that angle theta is called the power factor angle. And this triangle is called the power triangle. So now you see that there are three triangles that you need to know while doing the phasor diagrams. One is the impedance triangle, and that is obtained while doing the KVL, while solving the KVL, the Kirchhoff's voltage law. The admittance triangle, this is obtained while solving the Kirchhoff's current law, and then the power triangle. And one important thing in the power triangle, you have VA, you have VAR, and you have watts. This is the portion which is actually given to the load, that is the load component, the active power. This reactive power is actually put back into the mains, and this is the VA, or the resultant power, that is drawn from the mains, or the mains should be rated for, or the source should be rated for, and this is the power factor angle. This has very important implications, and one should understand that properly. Let us say, for example, I have the temporal coordinate system which is like that. Let us have a sine wave This is the voltage wave. Let us also have the current wave, and let me make the current lagging by some amount. So that current will lag by some amount, and this will come like that. Now let us get the power. This is of course the current wave. Now power is instantaneous multiplication of V and the I curves. Let me put some lines of demarcation. There is one point of demarcation which is this. This is another point of demarcation. There is one more important point of demarcation here within a period. Of course, so on it goes on. Here, if you look at the power during this period, what I have marked here, the current is negative, the voltage is positive. So when you multiply, the power is going to show negative. And during this portion, voltage and current is positive, and therefore it is going to be positive. During this portion, again, the voltage is negative, current is positive, and therefore the power value is going to be negative. And here both are negative, and therefore power is going to be positive, and so on. So which means if we have the power curve drawn along this line, you will see that at these points it is going to go negative. So, it will go negative, positive, negative, positive, so on. So, this much amount of area will get subtracted from this positive area, will get subtracted from the positive area, and only this much amount of area will on an average get passed on to the load. So, this much amount of extra power, extra VA is drawn from the mains, which gets put back in the following cycle into the mains, which is indicated by the negative power, which means the power is flowing back to the source. This is the power which is put back into the source, and that is the implication of negative power. So, this component which gets put back to the source is called the reactive power component, and that portion of the power which gets sent to the load is called the active. And on the whole, a resultant of so much, that is this plus the active, is to be drawn from the mains, and that is the VA. And the power factor theta here represents this angle, the power factor angle theta. What it implies is, if this angle is large, more negative component. In the limit when this angle becomes 90, the negative component of the power and the positive component will be equal, and there is no effective active power, which is so. When will it be 90? It will be when it is purely reactive, whether it is a capacitive or a inductive circuit, and if it is lagging, it is a pure inductive circuit. So, no power is put to the load, and all the power which is taken from the mains is put back to the mains, in which case this will be 0. That is when theta will be 90 degrees. The other extreme, when theta is 0, which means when the current is in phase with the voltage, power is always positive, which means everything goes to the load, and that is the active component. Nothing is put back to the mains. So, VAR will be equal to 0. So, the active power is cos theta into VA. This is the apparent power. So, the active power is cos theta or cos of the power factor angle into the apparent power. What this implies is, when theta is 0, cos theta is 1. So, active power is same as the apparent power. When theta is 90 degrees, cos theta is 0, active power is 0. So, if you want to have some active power, if cos theta is closer to 1, then VA is almost close to the active power. If cos theta is closer to 0, to get that same active power, VA has to be very high, which means the mains has to be rated that much higher. So, if cos theta is, let us say for example 0.1, and I want a 100 watt load, what it implies is that the apparent power that you should draw from the source should be 1000 VA. So, my source should be rated for 1000 VA to deliver a 100 watt load if the power factor is poor. This is called poor power factor. This cos theta is called power factor. So, this is an important concept that one should understand when dealing with sinusoidally excited circuits, and you will see this power factor more and more in future circuits, both in transformer circuits and the motor drive circuits, generator circuit, and so on and so forth. So, it is good to have a better understanding of this. Of course, in a later session, the next session, we will discuss more in detail about the power factor. Let us take a small example now to make our understanding a bit clear. Let us take a RL circuit for a change. There is an input source R L. Now, let us say there is of course a current I use an R of 5 ohms, and let us say you use inductance of 30 millihenry. Now, the question is, what is the frequency f of the source, and also what is the impedance Z? So, how do we go about doing this? So, we know that it is an inductive circuit, and therefore, the current lags the voltage. Let us take the current I as the reference. So, let us have the alpha axis along the I axis. So, which means you have I along this. So, the current lags the voltage. So, the voltage has to be in this direction, and let us say that is your voltage V I. So, there are two vectors, one in phase with the current, which is I into R, and the other orthogonal, which is I into XL, because this contributes JXL into I is going to cause anticlockwise 90 degrees rotation, and this is equal to I into Z, and there is an angle theta of course here. And let us have a further information here, and let us say for example that theta is given as 80 degrees. Now, we have the impedance triangle as this. R is 5, and therefore, Z cos 80 is equal to R. Therefore, Z is equal to R by cos 80. This is known, this is known, and therefore, Z is known. Or tan 80 is equal to XL by R. This is known, this is known, and therefore, we can find out this. So, once XL is known, which is XL equals R tan 80 degrees, which is equal to 5 tan 80 degrees. This is equal to omega L or 2 pi f L, and therefore, the frequency is 5 tan 80 degrees divided by 2 pi L. L is given 30 millihenries and all else is known, and therefore, the frequency can be calculated, and Z is calculated from this equation. So, this is how we go about performing the analysis. Just one more issue. Let us take an inductive circuit. L in parallel with R. So, here this is a current source now, this is an I which is coming in here, this is an L and this is an R, there is a node voltage V, there is a node voltage V. So, let us take the I direction as the reference direction, as the reference, and the voltage, the current has to lag voltage or voltage has to lead the current, and therefore, you have voltage which leads I. Now, along this voltage phasor, in phase with that is going to be V by R, which is the current here, and then there is an inductance coming in picture, and as we are talking of solving the Kirchhoff's current law, this is going to be the susceptance, inductive susceptance, which is minus JB, and therefore, it has to be minus 90 degrees. So, this is V by X XL, and this is V by Z. So, this is the G, this is the B, and this is the Y. This of course is theta, and the angle theta is given by tan inverse of B by G. Theta is given by tan inverse of B by G, or which is equal to tan inverse of R by X L. So, this is the admittance triangle for an LR circuit. We saw the admittance triangle for a RC circuit. It is good to know how it would look like for an LR circuit. So, like this, one has to construct the phasor diagram for any given circuit, whatever may be the complexity, based on only these two rules. For the KVL, you will end up with the impedance triangle, and for the KCL, you will end up with an admittance triangle. You can interchangeably use them, and as the circuit complexity progresses, the phasor diagram will gradually grow and build up from this simple triangles to more complex shapes. But of course, later on when we start covering transformers and induction motors and so on, we will see how these phasor diagrams will grow for more complex topologies of the circuit, but this is the basic that you should know about the phasor diagrams, especially for the R, RC, RL and RLC circuits. At this point, we will conclude the phasor analysis by summarizing that there are three triangles that you need to remember. One is the impedance triangle, the admittance triangle and the power triangle. The power triangle is a pretty important triangle in the sense that it gives good information about the amount of active power and about the amount of the reactive power that a particular circuit contributes, and what should be the amount of power, apparent power, that has to be drawn from the mains, which means what should be the source ratings. All this information can be gathered from the power triangle. The power factor angle theta is also a very important parameter which characterizes the circuit, which is actually a measure for the goodness of the circuit in many cases, and we will see more about the power factor in the next session. Thank you for now.